Cool, good. Okay. All right. So today we're gonna go over the second to last homework. So just as a overall note, there's no homework next week. Obviously, no office hours next week. Um, and then there will be just one more homework assignment the following week, and then the semester's over. So very, very close at this point. Congratulations, I guess. Maybe it's a little early for that, but stick with it. You're coming down the final stretch here. So chapter 14 is about fluids. The most common fluids basically are water and air that you'll encounter. I think all of our homework problems have to do with either water or air. And so there are some characteristics of fluids. One of them is just like the physics of like, how does a boat float, right? So a boat floats because you got a boat and it's submerged in the water. And what's happening here, the force is involved. We know that there is a weight that's going downward. You don't need to copy this down. It's just kind of an overview. We know that there's a weight that's pulling the boat downward that should be causing it to sink. The thing that prevents the boat from sinking is a force that you've probably heard of. It's called the buoyant force, and we'll call it F sub B. And the buoyant force just pushes up on anything which is submerged in a fluid. There's technically some buoyant force on you from the air around you. What we need to know, first of all, we get the direction. Cool, direction's good. The little more complicated part is how we actually calculate the buoyant force. So the technical definition of the buoyant force is that it's equal to the mass of the fluid that is displaced times gravity. There's the whole, the old, I don't know, folk tale of like Archimedes sitting in the tub and shouting Eureka and running around. That was the buoyant force. And you realize that you can calculate the buoyant force by considering the fluid that his body displaced when he sat in the tub. Now, actually calculating the mass of the fluid displaced, that's where calculating the buoyant force gets a little wonky. So, for one thing, it's weird to think of like taking a cup of water and weighing it, like how much water is in a cup, how much water is moved by a boat. Well, what we can do is we can use our definition of density. Remember, density is mass over volume. We used this, I think, once last week. We can use this definition, and the reason why we would like to use this definition is because we know that the density of the fluid, that's always like a constant. So for water, it's going to be 1,000 kilograms per meter squared, a nice round number. And we can then relate the volume of the fluid back to the volume of the object. That's a little bit more accessible to us than actually calculating the mass. So the first substitution that we'll do here is from looking at this equation. If I rearrange it a little bit, this tells me that the mass of the fluid will be equal to the density of the fluid times the volume of the fluid. So to go back over to this equation, this is much more, this is what you'll actually plug into your force equations, your Newton's second laws, when you're summing the forces, as you'll have that the buoyant force is the density of the fluid displaced times the volume of the fluid displaced times the gravity. So this is going to be the buoyant force that we are going to use this week. And then the actual problem solving, you sum your forces. So in this case, if I were to do my sum of my forces here, I would have the buoyant force up minus the weight down is equal to 0. And then what I would try to do is I'm typically going to know the density. In this case, it's if my boat is in water, it's 1,000 kilograms per meter cubed. And of course, I know G. The real problem solving comes in determining how the volume of the fluid relates back to the volume of the object itself. So in the case of a boat is partially submerged. So you need to know how much of the boat is under the water. In my picture, it's maybe 10% of the boat. So in that case, what you'll do is you'll replace the volume of the fluid with 10% times the volume of the object. And then we can usually calculate the volume of the object and go from there. So in this problem, problem number 1, that was supposed to be problem number 1, but we have just a little bit of an explanation there. In problem number 1, we're actually going to release a ball from rest at a depth. below the surface, and because the density of the ball is less than the density of water, what's going to happen is the water is going to push the ball up, and then the ball is going to shoot out of the water and go up to some height. So here's our water level, and we can draw a little ball down here. And maybe you wouldn't get it even fully submerged. It's hard to submerge something with a density less than water, but we'll release the ball. It's going to go up, and then it will emerge with some velocity initial, and then it's going to go up to some height, or y final. And so this part of the problem up here, this is just conservation of energy or kinematics, whichever one you want to do. But the thing that we need to get from our fluid consideration is we need to figure out what this final velocity, or I'm sorry, this initial velocity would be, which is the velocity as it emerges from the depth below the surface. They also do give us that depth. They tell us my depth happens to be 0.6 meters, but you're given a depth in the problem. Okay, so what we'll need to do is consider the forces on the ball. We know that there's going to be the buoyant force up and the weight down. And in this case, our ball is going to be accelerated, right? Because it has less density in the water, so the water is going to accelerate it upward via the buoyant force. And cool. Okay, so we have a picture here that we can use to set up, just as we've done all semester. We just want to treat this as like a free body diagram and go ahead and sum our forces in the y direction. And we have the buoyant force up minus the weight down, is equal to m times a. Cool. Nothing new here. The only thing that's new is we're calling this force a buoyant force, but it's just an upward force. We've had other upward forces before. Now we go ahead and replace the buoyant force. As I mentioned, you want to do mass of the fluid times gravity, but typically you're going to use this definition: density of the fluid times volume of the fluid times gravity. So I'm just going to go ahead and put that right here. Density of the fluid, volume of the fluid times gravity, minus my weight is mg. Now I have two different masses here, technically, right? I have the fluid, and then I also have the object. So maybe we should go ahead and label this the mass of the object times gravity, but it's still our mg that we're used to. And on the right-hand side, we'll also do the mass of the object times gravity. So just adding a subscript there so we can keep it straight. Okay. Oh, not gravity. That would be acceleration. All right. So far so good. Now here's where we have to do the new kind of problem solving part, which is to relate our volume of our fluid to the volume of the object in some way. And in this case, since the ball is fully submerged underneath the water, the volume of the fluid that the ball is displacing is equal to the volume of the object. The only time that you'd have a ratio would be if it's partially submerged. So I am allowed to just go ahead and replace then volume of the fluid with the volume of the object. Again, that's because my ball is submerged. Okay, now continuing on, we have the mass of the object. Sometimes we'll be given the mass of the object. In this problem, we are not given the mass of the object. All that we're given that relates to any of this is we're given a ratio between the density of the ball and the density of the water. So just as I did back here, where I replaced my mass with density times volume for the fluid, I can get a little crafty here and do the same thing for the object mass. So I now have minus density of the object, volume of the object times gravity. And on the right-hand side, I'll do the same replacement for m of the object here. So I have, again, density of the object, volume of the object times acceleration. All right, taking a look at our equation, you'll see that we have volume of the object in each one of these terms. So I can go ahead and eliminate that, get a little bit simpler. Now I have density for the fluid and I have density for the object. And as I mentioned, I do not know the density of the object, but I do know in my problem, it says the density of the ball is 0.4 that of water. So the problem gives me that the density of the ball, the density of the object, is equal to 0.4 times the density of the water, which in this case is the fluid. So in light of this, I can replace my density of my object, and now I have density of the fluid times gravity minus 0.4 density of the fluid times gravity, where I've just substituted out the density of the object. And then I will do the substitution on the right-hand side as well. So it's 0.4 density of the fluid times the acceleration. Taking a look at my equation again, do I have more stuff that will cancel? Yeah, I can go ahead and get rid of the density of the fluid. And I can combine like terms as well on the left-hand side. I have g minus 0.4g, which will be 0.6g. And then on the right-hand side, I have just 0.4 times a. So the fluid part is done. This right here, whatever your ratios are, you'll have 1 minus your ratio, and then you'll have the ratio on the other side. But this will give me my acceleration. And then I just have two motion problems to consider. I just have an acceleration over a distance. So that'll be a kinematics where my v initial is 0 down here. And I want to find that v final as it emerges from the water. And that will be your initial here. And then you can do, again, you can do either kinematics or conservation of energy to find the actual maximum height. So you just do those, again, those two motion problems. I trust that everybody can do those. So to keep moving through the homework. Okay. So the next problem is this very long-winded problem about some guy named Otto von Guericke. I probably didn't get that right. So he's got this like brass shell, and he essentially forms a vacuum inside the brass shell. And what happens when you form a vacuum is it's going to sort of resist being flooded with air. So the vacuum inside is seemingly pulling on that like brass shell on the outside. It seems like since you have a pressure in here that's approximately 0, and the pressure out here is approximately 1, what we call an atmosphere, which is the standard pressure of the atmosphere, which is 1.01 times 10 to the 5th pascals, which is what you will need to use if you do the calculation. Anyway, point is that because you've formed a vacuum like outer space inside of the shell, the pressure of the atmosphere outside is going to push in, and that inward pressure from the atmosphere around keeps the object intact. Now, a different application of this would be, say, a submarine, especially like a deep sea submarine, like Marianas Trench. I think it was that director James Cameron, I think, went down into the Marianas Trench in this crazy submarine. In that case, you have to be wary of this pressure difference because you have a really high pressure outside, and that really high pressure outside is going to crunch your submarine. So you have to build a strong enough submarine that it doesn't get crushed. So that's another sort of a similar problem. But in general, the physics that we want to do here is to consider the force that results from this difference in pressure. And so our rule is that if there is a difference in pressure over an object, then that pressure will be equal to a force that is applied over an area. In the problem where we're asked to solve, we're asked what force, we got these teams of horses, and we're asked what force the teams of horses must apply to pull the thing apart. Well, that's just got to be equal to whatever the outside force is from the pressure difference, the yellow forces here. In the problem that we have, since we are applying a force only sort of one-dimensionally, what we do is we set the difference in the pressure equal to the force over the cross-sectional area. And this is the only problem that you have to do with this concept. Yeah, so in order to find our force then, just to rearrange this equation, it'll just be delta P times a cross-sectional area. What is the cross-sectional area of a sphere? Well, it's a cross-section that runs through the middle of the object, um, perpendicular to the force, in other words. You can think of it that way as well, the area perpendicular to the force. So that's just going to be a pi r squared, where big R is the radius of the object. And they give you the radius, they give you the inside and outside pressure, or actually, let's see, they give us, they give us inside and outside pressure. They do give you the pressure in atmospheres. So for my problem, it happens to be 1 atmosphere outside and 0.12 atmosphere inside. So when I'm actually calculating the difference in the pressure, I'll do 1 minus my 0.12. I need to do a unit conversion. An atmosphere is not an SI unit. The SI unit for pressure is pascals, and the conversion is that 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. Again, the only reason why atmospheres is a unit is just because that happens to be the pressure in our atmosphere near the surface of the Earth. So just make sure that you plug this in as a unit conversion, and then you'll just do pi times whatever your radius is squared. Good question. Yeah, so I hand waved it a little bit, Nina, so that might be why you're confused on exactly where the delta P came from. Um, Another way of looking at this problem is that think about a can of soda before you open, or after you, well, think about it before and after you open it. How about that? So I've got my can of soda and it's closed, so there's no hole yet. And in this case, you can have some pressure inside. You can have like, let's say we have 2 atmospheres of pressure. Let's say we shake it all up. There's 2 atmospheres of pressure on the inside. And we know that outside, because we're just standing at the surface of the Earth, we know that we have 1 atmosphere of pressure outside. When I shake up the can of Coke, I'm increasing the pressure inside the can of Coke, and I can feel that difference in pressure because it's hard to squeeze the can, right? The soda, all the carbonation is now pushing out on the can. Once I open up a hole in the top of the can, then what happens is you open up a hole, and this lets the carbonation escape. And once the carbonation escapes, the can, you can now squeeze it, you can crunch it. Why can I squeeze it? Because what happens when the can is open is that the pressure on the inside is going to balance with the pressure on the outside. So the point is that we still have some pressure inside the can. We still have an atmosphere of pressure. The thing that caused this force is that there is a difference in the pressure outside and inside. So we consider the difference in the pressure in calculating the force, not just the absolute pressure. Let me know if that works for you, Nina. I could give a technical explanation if you'd like, but okay, cool. So yeah, all right. So it's just a concept. We will come back to actually, yeah, we will come back to pressure and force over area. And most of the rest of the chapter is going to be concerned with the idea of pressure. So if pressure's not clicking just yet, we're going to do some other problems that have to do with pressure. The next one in particular is you've got blood in an Argentinosaurus. I don't know what that is, but they call it a long neck gigantic sauropod. I not an archaeologist. Anyway, we will be modeling this dinosaur as a tube, a pipe, and maybe we'll go ahead and give and a little heart. And there's the heart and a dinosaur head up here. This is why everything is just a box I cannot draw. And then we have some feet down here. Oh man. Uh, okay. There's some feet. This is a big chicken. All right. So we have a circulatory system within this dinosaur, and it's a closed system. Thank you. Fighting for my life. It's a closed circulatory system, and what that means is that the pressures throughout the circulatory system need to all be correlated in some way. Now, what I will say is that the pressure is not going to be constant everywhere within this dinosaur's thing. So they give us that the pressure up at the head is, what is it in mine? 76.9 torr. And a torr is just another unit for pressure. Why do we have so many units? There's also another one that's like millimeters of mercury that you'll run into, which is also very annoying. Here's your conversion for a torr. 1 torr is equal to 133.3 pascals. Okay, give you all that. Help you out there. Okay, so they give us the pressure in the head and torr. It probably has something to do with biology. There's probably some biological reasons. Probably the unit they use in biology. Anyway, they give us the pressure up here, and in my case, it's 80 torr. And we know that blood is subject to gravity, right? Which is like why when something dies, the first thing that happens is that the blood like gathers in the lower portions and like the feet or whatever. Um, so yeah, so gravity is going to have an impact on blood, and it's going to impact the pressure as well. Um, the pressure is going to be greater down at your feet than it is in your head. If you are tall like me and you've ever stood up too fast and you get the fuzzies in your head, what happened there was you were laying so that your head and your heart were at the same level, so they're at the same pressure. And then when you stood up, you changed the height of your head relative to your heart. And so the pressure dropped in your head, and that's why your brain went all fuzzy. Um, so we have an equation that we can use to relate the different pressures. As I mentioned, they won't all be the same, but we can relate the pressure in one place plus this calculation, this little term, rho g y in that one place. This has to be the same as the pressure in a second place plus rho g y 2. The pressure plus the rho g times the y position, that is what has to remain constant. If rho gy looks like mgy, which was potential energy, that's good. You're kind of like going in the right direction there. That's exactly what's going on here, is that we're just sort of relating the potential of this fluid to the pressure instead of relating it to the energy. But it's more or less the same thing. So in this problem, we have different heights given. My head is at a height of 20 meters, and my heart is at 11 meters, and the feet, of course, at the ground will be at 0 meters. And we have the pressure in the head, and I think we just need to find the pressure in the other two. Yeah. So we will just, it's 2 parts. We'll just do 2 calculations with this equation. I'll go ahead and do the first one, which is to find the pressure at the heart, and the feet will be even easier than the heart because the y will be 0 there. Okay, so my pressure 1 is going to be the pressure in the head. That's 80 torr. I have to do 80 times 133.3, whatever that happens to be. So 80 times 133.3 plus the density is given in the problem, 1.06 times 10 to the third. Good point, Logan. So Logan just said that we have to give the answer in torr. That is correct. However, for this problem, let me make sure that I'm thinking of this correctly. Oh, yeah, so we have to convert either the pressure or the rho gy. So we'd either, if you wanted this equation to just give you an answer in torr, instead of multiplying the 80 by 133.3, you would divide your rho gy by 133.3 if you wanted to just get an answer in torr. You can also just convert back, which is sort of what I'm setting up here. All right, so the density is cool. The density is 1.06 times 10 to the third. Okay, I'm going to leave this as density because I'm going to run out of room. But anyway, this is density that's given times gravity times the height, which is 20. And then this will be equal to density pressure 2, which I do not know. Again, this will come out in pascals, plus rho g times y2. Y2 is just the height of the heart, which happens to be 11 meters. And plug in your rho, plug in your g, excuse me, and solve. And as I mentioned, you'll get a P2 you get some number in pascals, and then you need to divide that number by 133.3 to get your answer in torr. Yeah, the units are annoying in this chapter, but just again, I just always advocate for using the SI base unit whenever you're using an equation like this. Just always use your SI base units. You can always convert and convert back. And again, the SI base unit is pascals. So I would do all my calculations in Pascal. Okay. Problem number 4 is going to be kind of a similar calculation. It is, oops. It has a kind of a convoluted setup. It's again a very long problem to read, but here's the long and short of it. You have a mountain sitting on top of a continent, and it turns out, here's my mountain. It turns out that in order for a mountain to stick up, there has to be a root that descends down into the mantle. So this is all rock, all in here. And then we have mantle down here. And then, of course, above it, this is all just air up here. And right, so they give us some measurements here. The point is they describe this thing called the compensation level. And the compensation level is just this level way down in the mantle where every point at that depth has to have the same pressure. So they tell us pretty explicitly, I think, in a hint at the very bottom of that paragraph, if you read it, they tell us at the very bottom, set the pressure from A equal to the pressure from B. Now, what are we ultimately solving for? What we're looking for is we're looking for how deep of a root you would need to have in order to sustain this mountain of height H. That's the whole game. They give us that the continental rock itself has a thickness T, and then lastly, they say that the compensation level is way down here at a depth of Y below the continent, but above the root, not considering the root for that height Y. All right, and again, they tell us pretty explicitly, they say set the pressure at A equal to the pressure at B. That's our compensation level. I guess that's geology. Sounds good to me. All right. Now, A and B, in order for them to be at the same pressure, it means that all the stuff on top of them, which is pushing down on them, on those points, have to have the same pressure. So what is the junk that is above A? I have the mountain, I have the continent, I have the root, and then I have a little bit of mantle. So I'm going to add up all of those pressures, and for each one of them, I will have a rho gy, where rho will be the density, and y will be the height or the vertical length. Okay, so rho gy, so I have the pressure from, first of all, from all of the mountain plus the continent plus the mantle. That's all made out of rock. So it'll be the density of the rock or the continent as given in the diagram. Rho gy, so we need a g. And then the last part of rho gy is we need to know the y. Well, it's going to be d plus t plus h, or h plus t plus d, whichever direction you want to go. So h, I'll go down, h plus t plus d. And cool. And then there's also, above A, there's a little bit of mantle. Not a whole lot, but that little bit of mantle is just the difference between y and d. It's because y extends all the way up to the continent. So we also need to add in a density for the mantle, which again can come right off your diagram, times g, times whatever this vertical distance is. That's going to be y minus d. And yeah, cool. All right, so that is the pressure at A, and I apologize, I'm kind of running out of room, so I'm gonna have to continue my equation down below, do an equal sign here. This has to be equal to the pressure at point B. So let's consider the rocks that are above point B. We have some continent, that'll be a rho gy, where we have rho for the continent, g times the y here is going to be the thickness t, rho for the continent, g times t. And then we have plus, here we're going to have a little bit more mantle because there's no root above b. So that'll just be rho gy, where we're actually using y here as well. So this will be rho for the mantle times g times y. And yeah, I think everything here is given. Ultimately, we are solving for d, the depth of the root. So you'll notice that I have root here and d there and there. And what's the question? What about the piece of the mountain that's above b? The mountain, excuse me, in this like very like rectangular diagram, this right here is the mountain. So that is only above A. There's no mountain above B. This is all just air next to the mountain. Anyway, yeah, so I think you have everything in this equation except D, and I'll leave, yeah, cool. Leave that solution up to you. Y was, I think, just double check. They give you the mountain has a height, cotton, and they give you H, they give you T, and the Y will cancel because you'll have rho for the mantle gy on the left-hand side and rho for the mantle gy on the right-hand side. So the Y terms will go away in both of them. I have to convert the density from grams per centimeter to kilograms per meter. It's a good question, and yeah, you would get, I'm trying to think of what units, you'd still get some sort of meters. Like it might come out as kilometers if you don't convert. I can't do the calculation in my head, unfortunately, even though I have an answer. But what is a gram per centimeter to kilograms per meter? Let's see, you'd have 1 kilogram has 1,000 grams, and then 1 meter has 100 centimeters. So you end up, it's what, 1/10. If you multiply grams per centimeter by, 1 on 10, then that'll give you kilograms per meter. So I guess if you didn't convert it, the answer that would come out would be decameters, which probably aren't very useful. Also, make sure you can convert your answer to kilometers at the end. All right. Next one. What are we doing here? Yeah. Oh, okay. This one, just as a forewarning, there's going to be an integral. All right. So here we're actually investigating the atmosphere itself, and the atmosphere has a height. Obviously, we know that at the surface of the Earth, we have 1 atmosphere of pressure, and we know that in outer space there is a pressure of 0 atmospheres. There's no pressure. It's a vacuum. Don't open your helmet in space. And in this problem, they ask us to investigate. They ask us to actually find the height of the atmosphere. And the only consideration that we need to take into account is how the density of the air changes with height. So part A shouldn't be too much of a struggle. In part A, we're allowed to just treat the air density as if it's uniform. So we're going to go from the surface of the Earth down here up to the height where the atmosphere ends. So we have all the atmosphere inside of here. And this will be 0.1, and this will be 0.2. And I know that the pressure at 1 plus the rho gy at 1 has to be equal to the pressure at 2 plus the rho gy at 2. Whenever there's a height consideration with pressure, this is the equation to go to always. How does it work out in this particular problem? At 0.1, we are at a height of 0. So this term will go away. And at 0.2, we're at a pressure of 0. So this term goes away. And we just have that pressure at 1, which is 1 atmosphere, has to be equal to rho g times the y at 2. And then we just go ahead and plug in our 1 atmosphere times the conversion factor of 1.01 times 10 to the 5th pascals. It'll have to be equal to the density of the air. Mine's given it 1.35. I think everyone might actually have the same thing in this problem. And my G is 9.8, and I just solve for Y2. All right, so that part, part A, is not too tricky. And the reason why it's not too tricky is because we're allowed to treat the density like it is the same all the way up the atmosphere. Now, in truth, what happens, especially if you've ever been up to a mountain, you've experienced this perhaps, that the density of the air is going to change as you go up to a higher height. How do we know that the air density is uniform? It's not just, we didn't cancel because the air density was uniform. Regardless of how we were treating the air density, Y1 is 0 because that's the ground. So that's why this term goes away. And the pressure at 2 is 0 because that's outer space. So the pressure in outer space is 0, which is why that term goes away. Okay, yeah, so as I mentioned, also, yeah, so the density of the air actually changes as you go up to a higher elevation. And so our calculation here is going to be impacted a little bit. Instead of simply calculating, rho gy2, we actually need to consider the density at each height as we go up. And they tell us to model it as if it decreases linearly to 0. So we want to write an equation here, which will have a density at y equals 0. That is equal to 1.35 kilograms per meter cubed. That's the density of the air that's given in the problem. And we want this to decrease linearly so that the density at y equals space, whatever space is, that's ultimately what we're looking for, right? But we want the density when we get to space to be equal to 0. And we want this to be a linear decrease. So to write this as an equation that we can integrate in terms of y, our density is going to be 1.35, whatever the density of air is, that's our y-intercept, minus, we could say y here, and I'm trying to decide if I want to correct it by h or not. I don't know how accessible that is. I think we'll do, yeah, so we're going to do y over h, and then what will we have? Yeah. So we want, as y goes to the height, we want this to go to 1. So this will be, one sec. Okay, so we want to call this location of space. We need to give that an actual letter, a variable that we can solve for. So we'll go ahead and call that h. And then we know that we want this equation to go to 0 as y goes to h. So we'll have 1.35 times 1.35 minus 1.35 times y over h. So this is how we tell it to decrease linearly. I know it's maybe a little convoluted. This is how we tell it to decrease linearly down to 0 when we hit whatever the height happens to be, whenever y is equal to h. Okay, so to simplify this a little bit, to give us something that's a little cleaner to integrate, what I'm going to do is I'm going to factor out that 1.35, and you could call it density naught or something like that. That might make more sense. Or you can call it 1.35. I'm going to call it just density naught so that I can plug it in easily to an integral. And then all that I'm left with in the inside is 1 minus y over h. And this is an equation now in terms of y. My variable is y for the density decreasing linearly. And we've written that equation ourselves. Now, to go back to this equation, instead of simply saying that the pressure at 1 is equal to rho g times the y at 2, since my density is variant, and my density is varying with my my height, I instead have to say that the pressure at 1 will be equal to the integral of rho g dy as I integrate from 0 up to my height of h. To be very mathematically particular here, as we will need to be next semester as we do a little bit more integration work in physics 2, I need to integrate anything that varies with the height. So I need to integrate rho or g. In this problem, they do give us a break by saying that we are allowed to treat, oh, they don't even actually say it explicitly, but you're allowed to treat g as if it is constant. We know that it wouldn't be, and so you could dream up a nightmare scenario where you'd have to write g and your gravity in terms of y using the universal gravity that we did last week, and then your density as well. In this problem, we don't need to do that. We are only going to integrate one thing. We're just going to integrate the density. So pull your g out, and then we have the integral from 0 to h of our equation that we've just written, rho naught times 1 minus y on h dy. And I can integrate that. I know my rho naught will come outside, so I'll have rho naught g. And what is the integral of 1? The integral of 1 will be y, which will give me, when I evaluate my limits, well, let me just write the integral. So we have y minus y squared on 2h, and we need to evaluate it from 0 to h. Obviously, when I plug in the lower limit, 0, I'm not going to have anything that survives. And when I plug in the upper limit of h, I'll have, running a little out of room here, I'll have rho naught times g times h minus h squared on 2h. Again, that's a minus sign right there. So I've just evaluated my limits. Notice that I have an h squared on h. That'll simplify a little bit. Now I have h minus h on 2. What does that give me? That just gives me an h on 2. And so this will give me rho naught g h over 2. And there we go. We've performed an integral. We're very proud of ourselves. And now, instead of having rho gy2, we'd replace it with this guy right here, because this is the value of our integral. So you, again, just set this equal to pressure 1, and then plug everything in. Of course, perhaps uninspiringly, the answer happens to be to just divide rho gy by 2. But anyway, that is the proof behind why that is. All right, one little calculus problem, and then go back from there. Oh, ultimately you are solving for the height of the atmosphere. So you set pressure 1 equal to rho gh on 2, and then you're going to solve for h right there. So you have h is equal to 2 pressure 1 over rho naught g. Okay, our next problem has to do with hydraulic. You might have heard the term hydraulic before. Hydraulics is like a form of a piston that has a sealed tube or something to that effect, or some sealed system where there's some fluid inside, and that fluid has to be at a constant pressure because your thing is fully sealed off. And you can do a lot of cool things with hydraulics. A common one is like a hydraulic lift, where you have like a piston that pushes up, say, a car or something even heavier than that. In our problem, we're going to use a very simplified example, where we have something like this. And the key, as I'm drawing this, the key is that your openings have to be of different size. So we have a wide opening on the right-hand side, and we have a skinnier opening on the left-hand side. And the rule is that the pressures are going to be the same. So you have location 1 and location 2, and the pressure at 1 has to be equal to the pressure at 2. And that's because we have, again, a bunch of fluid in here. So, all right, so now ultimately the whole point of a hydraulic press or hydraulic lift or anything like that is that I can put force in one side, and because the areas are different, I'll get out a much greater force than what I have to input. So we are again going to use the pressure equals force over area that we used, I think, in problem number 2. So pressure 1 is equal to pressure 2 becomes force 1 over area 1 has to be equal to force 2 over area 2. And so this means is that as I increase my my area, I will increase the force that is output over that area. All right, so the problem gives you each area in terms of some constant a sub I, but I give you the area of each, and they're also going to give you sort of the two forces that are involved. On the left-hand side, we're pouring sand. We're pouring kilograms of sand in over here. So the force on this side is going to be a mass times gravity. That'll be our force 1. And on the right-hand side, we're going to be compressing a spring. So force 2 is going to be a K times X. It isn't always that way. It's usually you're going to just like apply a force on one side to receive some force out the other side, which is, I guess, what we're doing here with the sand. All right, and so we can go ahead and plug everything in here. In my problem, I'm told that the area 2 is 16 times area 1. So they say that this is A sub I, and this is 16 A sub I. And yeah, that looks good enough. I think we have everything that we need here. Go ahead and replace your force 1 with mg, and replace your area 1 with A sub I. Replace your force 2 with kx, and replace your area 2 with whatever area they happen to give you. Mine is 16 A sub I. We can cancel out A sub I from both sides. Ultimately, we are asked to solve for the mass. So if I divide both sides by the gravity, I have that my mass is equal to kx on 16g. And they give me a spring constant in the first line. They give me a compression distance in centimeters in the last slide, so make sure to convert that to meters. But you can go ahead and plug those into the top of the right-hand side, and then you plug in your 9.8 on the bottom, and that will give you your mass for this problem. Okay, and that's just one like application, but there's always a question on that, and it would be a good candidate for an exam question, definitely. All right, problem number 7. In problem number 7, we have a graph, which might be scary. We also have a new term, apparent weight. So we need to, I guess, discuss what apparent weight is, but just to talk about the problem, you have a block, and you're going to press down on the block, and here's your block. The block is in the water, and you're going to press down, and as you press down, the block will become more and more submerged in the water. And as it becomes more and more submerged, the buoyant force is going to increase. Why do I know that? Remember, the buoyant force is the mass of the fluid times the gravity. Okay, so here B gives the apparent weight as a function of the depth of the lower face. I see. Okay. I lost my track real quick. Let me get it back real quick. Yeah, so we have a buoyant force. The buoyant force is going to change, of course, because as you push the block further and further under the water, the mass of the fluid that is displaced by the block increases because more and more volume of the block is underneath the water. What they want us to solve for is they want us to solve for the apparent weight. So where does the apparent weight fit in? What is that definition? Well, I know that I have a buoyant force acting upward, and there is some weight, some mg acting downward. And this stuff would balance out if it weren't for the fact that I was also applying a force. And that force that I am applying is what will be the apparent weight. In other words, it's technically it's equal and opposite to the apparent weight, but that is sort of good enough for us, I think, to say that we'd have, yeah. So yeah. So we'll go ahead and just say that this is our applied force. And we'll say that that applied force, as I mentioned, is going to be equal and opposite to the apparent weight. The apparent weight is just like what you would measure if you were to apply a scale to this object. So anyway, so we're going to go ahead and do the summing of our forces. And we'll have the buoyant force upward minus the apparent weight minus the weight. and this will be equal to 0. And we have our buoyant force. Remember, buoyant force is mass of the fluid times gravity, which we've said is going to be density of the fluid times the volume of the fluid times gravity. And then we have the apparent weight. Since we want to solve for the apparent weight, I'm going to move it over to the right-hand side. So I'm just going to be left with my mg down minus mg. This will be equal to the apparent weight. Actually, sorry, we're given an equation. I'm sorry, we're given a graph for the apparent weight. What are we ultimately solving for? Oh, we're looking for the density of the fluid. Okay, so I'm going to leave the apparent weight over here. So I have minus the apparent weight minus the mass of the object times gravity. That's our mg. This will be equal to 0. All right. Now, in order to, let's see, in order to calculate ultimately the density of the fluid, we need to know the weight of the object itself. And the weight of the object itself will come from the graph. So the graph looks something like this. We have, they're going to give you an intercept, and then the actual graph does something like this. I believe everyone's going to have the same graph. So the important things here are that the weight of the object is the y-intercept up here. So that's going to be 5/4 of whatever the scale is of the graph. So right here, your W will equal 5/4, 1.25 times whatever that WS is that they give you. And then the other important point is where the object becomes fully submerged. So the object becomes fully submerged when this graph goes flat. That occurs at an H of 1.5 centimeters. And that value happens to be 1/2 of WS. So WS on 2, whatever value they give you again. Okay, so those are the two important values that we need. And we can go ahead and plug them in. As I mentioned, this is going to be our weight. So that's going to go right here. That's actually, I didn't even need to do m object times gravity. I can just plug in that entire weight right there. And the apparent force is going to be this guy right here. And that's going to correspond to a certain volume that's submerged. And I'll talk about that in just a second, but let's go ahead and do those few substitutions that I just traced out. So we have density of the fluid times the volume of the fluid times gravity minus the apparent weight. That's going to be the W scaling over 2, and then minus this weight right here, so minus 5/4 times the weight scaling. My signs are not going to work out here. Apologies, in just 1 second. I can explain why I'm about to do what I'm going to do physically. Okay, so a better way of looking at the apparent weight than what I've done here in terms of the applied force, a better way of looking at the apparent weight is to consider it as just the difference between the weight and the buoyant force. So this graph tells us that, for instance, when you're not submerged at all, you have a weight up here, 5/4 times the scaling. And that would just be equal to your mg. And as you submerge more, the buoyant force is going to cancel out some of your weight until you reach this like terminal buoyant force. But that just means that this is just a difference between the weight and the buoyant force. So the way that I should have set this up is that this is however much weight is left over once you've accounted for the buoyant force. So in other words, it's going to be the MA on the right-hand side. And it is going to be negative, but the way that I should have written this equation is that I should have put, again, an MA on the right-hand side. And I should have considered this apparent weight to be, again, the resultant. So the net force would be your apparent weight. That would be your MA. So let's go ahead and just fix these equations here. Again, I'll have an MA. This hasn't changed. The only thing that's going to change is now instead of having the minus on the left-hand side, I do have to say, okay, the apparent weight's going to be a downward force. It'll have a magnitude of WS on 2, but since it's downward, that's going to be minus WS on 2. Okay, and now to consider these signs, yep, everything should work out here, and we will get a positive value for our density. Good, okay, so the last thing that we need to do is we need to get rid of the volume of the fluid. Remember, we often want to replace volume of the fluid with the volume of the object. In this case, since we're considering once we are fully submerged down here, that means that the volume of the fluid is going to be equal to the volume of the object. And then the last thing is the way that we actually calculate the volume of the object is that they give us the what is it? The bottom and top, the face area. They give us a face area in the problem. So a volume of a block can be written as just the area of one face times the third dimension times the length. In this case, that third dimension is this value on the graph, right? Because that's this height right here. That'll be your H. And then we know the cross-sectional area. So our total volume will be the area that's given in the problem times that H, which is it's 1.5 centimeters, but I'm just going to write H. And this right here is what we'll plug in for the volume of the fluid, and then ultimately we have everything else that we need to just solve for the density of that fluid. All right. Cool. All right. I'm going to go ahead and leave this problem and keep going now that I've sufficiently chased my tail. And I believe it's the last 3 problems are all going to be on fluid that is in motion. So first of all, we had a pressure comparison that had to do with height. And that pressure comparison that had to do with height said that the well, okay, we're not there yet, actually. In this case, we're literally just looking at flow, just flow rate. So if I have a pipe, I got a big pipe that's feeding into a smaller pipe, and this would be like section 1 and section 2. What's going to be constant between these two? If I have water that flows through my big pipe that then enters into the smaller section, all the water that flowed through the first section has to flow through the second section. And it has to do it in the same amount of time, or else you'd have like some weird like bunching up or something like that, right? So this is called the volume flow rate. We just call it R. The volume flow rate in 1 has to be equal to the volume flow rate in 2. So in problem number 8, in part A, you're given that there are 3 smaller pipes feeding into a third, and they give you the flow rates in liters per minute in the first 3, and they ask for the flow rate in the fourth pipe. Since all of those pipes are feeding in, since you have something like this, all the water that comes from each one of these pipes has to flow through our third pipe. So through the fourth one rather. So you just take each of these, if it's like 10 liters per minute and 12 liters per minute and 5 liters per minute, then the rate through here has to just be 10 plus 12 plus 5. That's it. You just go ahead and calculate your flow rate. It'll be the same units in and out. You don't even need to worry about units for part A. For part B, they ask us to calculate something to do with the speed. So how does speed factor in here? Well, this is a rate, and the units might give you a clue that it's liters per minute. Liters per minute tells us that it's volume over time. So that's why it's called the volume flow rate. So your volume flow rate is volume over time. Typically, we won't use this definition exactly. We'll use a little bit of a modification, which is that we could consider that the pipe has a cross-sectional area, and replacing the volume with the cross-sectional area times the distance that the object has to travel, you then have, you don't need to write this down, this is just an intermediate step, but you'd have an area times some delta x over the time, which is technically a delta t. And considering delta x over delta t, we have a definition for that. That's velocity. So your volume flow rate can also be written as area times velocity. And this is the thing that we'll set equal when we are setting the two volume flow rates equal to actually solve a problem. So in part B, they just asked for the ratio of the speed in one of the pipes to the speed of the water in the final pipe. Yeah. In terms of the speed in one of the other ones. And cool. So I know that these three volume flow rates have to be equal to the volume flow rate here, the sum of those. So calling those each 1, 2, 3, and 4, we have rate 1 plus rate 2 plus rate 3 is equal to rate 4. And I already did this calculation for part A. Now I can go ahead and, okay, I'm back there. Can everybody hear me? I know I could get something in the chat. I can't believe, I swear if I just lost that recording, I'm going to be very upset. Okay. Am I back? Am I back there? Okay. I am now having, appreciate everyone sticking with me. Okay, I believe everyone can hear me again. And I hope you can see the whiteboard. I am getting feedback. This is incredibly annoying. Why won't, okay. I wish, yeah. My computer just fully freaked out. I don't know what's going on. I really hope that I didn't lose that recording because then I'll have to do it all over again. Okay, what was I talking about? Problem number 8. All right, so we have, so we have these 3 different pipes, and we're talking about part B. Okay, and we had specifically that the rate of 1 plus the rate of 2 plus the rate of 3 has to be equal to the rate of 4. And they then asked us to, they just want a ratio of the speed of the water in one and actually in four to one of the other ones, specifically the one that's carrying 25 liters. So in that case, we just do like the rate of 4 over the rate of whichever one is carrying the 25 liters per minute. So that would be whichever. Okay, just call it whatever. Call it 1. So the flow rate through 4, well, we know the flow rate through 4, we know the flow rate through 1. So we know this is going to be whatever our answers were. I had made up some numbers, but mine would be 54 over, they say they want the 25 liter pipe. Okay, so I know the value of that ratio. I also know that each of these rates is an area times a velocity. So I'd have the area of 4 times the velocity through 4 over the area through 1 times the velocity through 1. And they ultimately, they ask us for the speed, the ratio of the speed of the water. They want the ratio in the 1.8 centimeter pipe to, so they want us to solve for this ratio right here. So I'm going to leave that stuff on the right-hand side, and I'm going to multiply by the reciprocal of this ratio to get it over on the left-hand side. And so that'll give me 54 on 25 times the reciprocal of that would be area 1 over area 4. And then that's going to be equal to V4 over V1, which is what we want to solve for. All right, so far so good. The last thing we need to do then is replace these areas. Each of these areas will be pi r squared. Area 1 will be pi times the radius of the first pipe. The first pipe is one of the 3 pipes that are going in. These all have, in my problem, it's 1.4 centimeters. Excuse me, so that's 1.4 centimeters. Make sure I convert that to meters squared. And then the area through pipe 2, for me, it's 1.8 centimeters. So it'll be pi times 1.8 centimeters squared. And that's, I guess I called that 4. So that's 1 and that's 4. And we just go ahead and plug each of those in and evaluate, and you'll have just some number on the left-hand side, and that will be your ratio. But again, the most important thing for this problem to know is that the speeds will be different through the different pipes, but that the area times the speed is the thing that must remain unchanged. Okay, so okay, so I started to explain this. Now my internet is about to make me lose it. I started to explain this and then I backtracked. But I was talking about the speed of water that's flowing through a pipe. And just as we had a consideration for the height, and as we go to a greater height, there's less pressure, there's also a consideration for speed. As fluid moves at a faster speed, it's actually going to be held at a lower pressure. So just as we had a rho GH that looked like an MGH, we can also do something with the 1/2 mv squared. And it's going to look like this, just pressure in one section plus 1/2 rho V1 squared. Are you really? Rho V1 squared has to be equal to the pressure in a second section plus 1/2 rho V2 squared. And this works for a pipe like the one that we have in our problem, where we have a big section going into a small section. This will be section 1, and this will be section 2. Now, we have 2 things that are going to relate. We know now the volume flow rates would be the same. We may or may not use that. I don't even know if we're going to use that in this problem just yet. But we do know always that the volume flow rate through 1 will be equal to the volume flow rate through 2. And the reason why that would be useful is because this means that the area through 1 times the velocity through 1 has to be equal to the area through 2 times the velocity for 2. Why would this be useful? Well, because we have a consideration of those 2 velocities here when we're talking about pressure. So this can often be useful even if we're not going to use it in this particular case. What are they going to ask for? They're going to ask for the rate of water flow in cubic meters per second. So they're actually asking us to calculate a volume flow rate. So I don't think we're gonna use it to solve the problem. But what they do give us is they give us both areas, they give us both pressures, and um, and that's it. So if I have uh, both of the areas, yeah, okay. So I have the areas. So I am going to use this relationship here. I have both the pressures P1 and P2. That's fine. I ultimately want to find one of my two velocities. So I actually have everything here that I need. Just to give you an idea, let's see, I have 53 kilopascals and we'll do 50 kilopascals and 40 kilopascals. A kilopascal has to be multiplied by 10 to the third. So I'd have 50 times 10 to the third plus 1/2. My rho will be the density of my fluid, which is mm, yeah, okay, so I don't have a density. I remember. Okay, I remember where I'm going here. My answer will ultimately be in terms of the density, but that's fine. Um, so, oh, no, we're given that it's water. Does it say water somewhere? Well, regardless, it is supposed to be water. So the density is supposed to be 1,000. All right, and then for either V1 or V2, I need to replace one to be in terms of the other using this equation right here for the purposes of this. Um, oh, it does say, oh, rate of water flow. Cool, thank you. Yeah, there's just too many words. The last line there, water, good. So I'm gonna go ahead and replace V1. And in light of this equation, it would be that V1 is A2V2 over A1. So A2V2 over A1. That quantity is going to be squared. Keep in mind that I do have A2 and A1, so I could plug those in. And this will be equal to the pressure in 2, which is 40 kilopascals. So that's 40 times 10 to the third. And then I have plus 1/2 times rho, which is 1,000, times speed 2 squared again. So again, my areas are given. Make sure that you plug in the correct ones. Um, the the way that I have it set up, the second one would be the so-called throat. So area 2 would be the throat cross-sectional area, which is mine's 31 centimeters squared. So I'd have here I'd have 31, and down here I'd have 62. And then the only unknowns here are my V2 squared. So I just need to do the little bit of algebra here to solve for V2. Okay, so cool. So we have these two ways of relating pressure, which is that the pressure will change with the height, and then also here we see the pressure will change with the speed. And the last thing that we can do is we can put those two concepts together, and this is sort of what we've been building toward, and it's building toward this big equation called Bernoulli's principle. What is the symbol? The 62. The 62, oh, that's supposed to be an A1. That's the area of this pipe. And then the A2 is on top. Cool. All right, so Bernoulli's principle, again, just relates the pressure at two different locations to a to both a height and also a speed. So you have the pressure at one location plus the rho g y1 plus the 1/2 rho v1 squared. Why does it keep? Okay, and yeah, so you can set these equal for any 2 points, which we're going to do in this problem. So you have P2 plus rho g y2 plus 1/2 rho v2 squared. And in this problem, we are asked to find, we're going to poke a hole in the side of a tank, and then the water is going to flow out, and it's going to flow some delta x. And that delta x will just be a motion problem. Once the fluid is out in the air, it's just motion. So the only thing that we need to consider is what is going on inside the tank. So we have a pressure at the top. The tank is open, so we have some pressure. Let me draw a little sketch. All right. Oh, yeah, sorry. There's one more step on that problem. You're ultimately, yeah, with this equation, you're solving for V2. And then I believe they ultimately asked on problem 9 for um, the flow rate. So what you do is once you find V2, then you'd calculate the flow rate, which is equal to excuse me, A2 times V2. So once you find V2, then you can plug it in there. Yeah, and you also have a V2 on this side, if that's not clear. All right. So yeah, so here's our problem. We're going to drill a hole in the side of this tank. It's a height h, and below the water level, and then the water is going to shoot out. And I know that I have 2 different pressures. In fact, the pressure up here is 1 atmosphere, and the pressure out here is also going to be 1 atmosphere. So that means that pressure 1, which is up here, is going to be equal to the pressure down here at 2. So pressure 1 and pressure 2 are going to are equal. They'll cancel out. Up at 1, we are up at a height of big H. Let me use the same color. It tells us that the water height is big H. The whole height is little h. So we could replace our y1 with rho g big H. And there's not going to be any velocity up there. So this term will go away because that v1, it's 0. And then this will be equal to rho g y2. What is y2 is this hole right here, which is at a height of big H minus little h. So that'll be rho g big H minus little h. And then we have plus 1/2 rho v2 squared. And we could simplify here. You could have also just done like a difference in the heights, which is little h if you want to, but I'm just sort of being robust in my approach here. My rho is going to cancel out of each of these terms. And then I have gh minus g big H plus g little h. So that will just give me a g little h on the left-hand side is equal to 1/2 v2 squared. This isn't going to look any different than what we've solved for before. You ultimately get that v2 is equal to the square root of 2gh. That should look identical to some calculations that we've done before, which is good. That means that the physics checks out. And in fact, in this instance, you can treat the water as if it functions like motion. And then for part A, they asked for the distance at which it's going to hit the ground. So you would then do kinematics here. This is going to be your initial velocity in the x direction. So you do your x and y, and you'd have a velocity in the x of root 2gh, and that's not going to change. You just have delta x is what you're solving for, because velocity times time. Of course, we need the time to come from the y direction. So you just have the acceleration of negative 9.8 in the initial velocity of 0. And our delta y ultimately will be, and this is where you want to relate it back to the different heights here. This is our delta y. Notice that this is my height big H minus my height little h. So that'll be big H minus little h. Each of those is given. So for part A, each of those is given. And you can just plug in the actual numbers. In part B, they ask us to solve. Okay, one sec. Let me take a look at it before we go to part B. Yeah, how did I cancel everything out? Yeah, let's take it one step at a time. First of all, the hole is drilled here, so the pressure will be balanced inside and outside of the tank. So the pressure up at the top of the water and the pressure down at the hole will be equal. I don't know what they are, but I know that they'll be equal, so they cancel out. There is no velocity in the water at the top of the tank. That water is just sitting there. So 1/2 rho v1 squared will be 1/2 rho times 0 squared. So that term goes away. And then we replace our y1 and y2 in terms of the big H and little h from the diagram. And all of our terms in this step all have a density rho. So at this point, I go ahead and cancel out that density rho. And then I have g times big H minus g times big H minus little h. So the g times big H cancels there from the subtraction, and we're just left with minus negative g times little h, which just becomes this little gh right here. Cool. All right. Yeah, so part A, plug in your numbers, you're good to go. For part B, excuse me, we're asked to drill a hole to give us the same depth that we get from the hole at the top. And for this particular one, we would need to write a general equation for an h that would give us this constant x that we have found. And so let's write a general equation here for delta x. And in order to do that, I need to do a little bit more of the kinematics here. I'm going to do this on the next page, but keep in mind we have this equation that ultimately led to this stuff. And so for my x equation, I'll have delta x is equal to this velocity times time. So delta x is equal to root 2 g little h times time. And then I would get a delta y equation that's going to be big H minus little h. Actually, that should be negative out in front of that whole thing too. So it'd be little h minus big H is equal to negative 1/2 g t squared. So little h minus big H is equal to negative 1/2 gt squared. And we could cancel out those negatives if we'd like. But we are going to have to, I guess, cancel out the negatives and take the square root, solve for the t here, and we get that t is equal to the square root of 2 on g times big H minus little h. And I can plug this into the equation up above. And when I do, I'll have delta x equals the square root of, I have a 2 and a 2. That'll give me a 4. I have a g on top and a g on bottom. Those will cancel. And then I'll have a little h times big H minus little h. All right. So ultimately, this is essentially one root. Hold on. How did they get? Oh, let me make sure that. Yeah, okay, I can pull the 4 out, take a square root of 4. Ultimately, this gives me one result. If I plug in big H and little h and solve, then I'll get my answer for part A. For part B, we are asked to find another height that would have this same delta x. So we are solving for some second little h that would satisfy this equation. And in order to do that, what we would like to do is find the roots of this equation, which we can do by turning this into a quadratic and solving for the roots. So how will that function? Well, the most straightforward way to turn this into a quadratic is to square, and we would square both sides. And this will give me a delta x squared on the left-hand side, and on the right-hand side now I'll have 4 times little h times big H minus little h. Just cancel out the square root. Now I'm going to go ahead and distribute my 4 little h, and I can also move my delta x squared over to the right-hand side. So subtracting that, I have negative delta x squared. What I have when I distribute here is I'll have 4h times little h times negative little h will give me negative 4 little h squared, and then the other term would be 4h times big H. So I'll have plus 4 little h times big H. And now I have a quadratic that I can solve. This quadratic will give me 2 different roots, and the roots will ultimately be what do we ultimately get here? So sort of skipping ahead just a bit, if you do your quadratic equation and solve, you'll get that little h is equal to big H plus or minus the square root of big H squared minus x squared all over 2. And what this tells me is that little h would be equal to either the positive root or the negative root, but by solving here, we can relate these two and see that little h 2 would be equal to big H minus little h1. So in other words, the quadratic is symmetric is another way of looking at it. So we have plus or minus the 2 different roots. The net result here is that, to go back to our drawing, one of our solutions, our first solution for part A, is little h measured from the top. Our second solution is just little h up from the bottom. So that would just be your other solution. And so for part B, I think they ultimately ask you for what depth the second hole should be. So the depth is going to be big H minus little h, which you can just calculate right from what's given there. I realize that I didn't give a great solution there, but that will be ultimately the answer. And then the last part C, they ask us to maximize our x value. So I had an equation for x right here that I squared. If I would like to maximize this before I squared it, then I would, of course, to maximize, you're going to take a derivative, set it equal to 0. So again, this equation was, just to copy it down, x is equal to the square root of 4h times big H minus little h. And if I want to maximize this equation in part C, I differentiate. set it equal to 0. So my x prime, the derivative of the outside is going to be 1/2 times, oh, I mean, it's probably actually even easier to just differentiate the square of it. So because it's all positive. So x squared is 4 little h times big H minus little h. And then, yeah, just go ahead and differentiate this with the product rule. So sort of hand waving here, but call this x squared prime, because x is all positive when it is at a maximum, so let square b. Derivative of the first is just 4 times the second h minus h plus the second times the derivative plus the first times the derivative of the second, which is 4 little h times the derivative of big H is 0, derivative of minus h is minus 1. And so this is 4 big H minus 4 little h. I've just distributed here, minus 4 little h. And this will give me 4 big H minus 8 little h. And ultimately, I wanted to set this equal to 0. And if I do, I solve for a little h that is equal to 1/2 of the entire height. In other words, how do I maximize my x distance? It's actually to drill a hole in the middle of the tank, drill your hole right in the middle. And that's the perfect balance between the depth that gives you more initial velocity and the height that's left over so that you can get more projection. So again, to show you what would happen with this tank, now that we've sort of drawn this entire picture, here's my tank, here's my water level. If I were to drill a hole right at the very top, the water would not have enough pressure to come out, so it would just dribble down. As I move downward, the water is going to go further and further and further until the middle, where there's a maximum, and then it would start to come back. And in fact, it would be a mirror image of how far it went until you get down to the very bottom, at which point it's just going to dribble out onto the ground. Cool. And yeah, that's the picture of that problem. It's just a very common problem. It's been a homework problem forever. And that is the end of that homework assignment. That went on for quite a little bit, but I'll go ahead and stop the recording. If you have any questions, feel free to stick around.